Hello, everyone, and welcome. Today, we're going to walk through a developer's guide to Verisense, focusing on the core task of deploying and then interacting with a simple Nucleus. By the end of this session, you'll understand the basic commands and concepts needed to get your own application running on the Verisense DevNet. We'll start today's session with the environment setup. Before we can deploy anything, we need to make sure our development environment is ready. This includes installing the Rust toolchain and setting up the WebAssembly target, preparing the Verisense CLI tools that we'll use for managing Nucleus deployments, and optionally, running a local Verisense node for development purposes. Once the environment is ready, we'll move into the core part, deploying a simple Nucleus onto the Verisense network. This process consists of two main steps. First, we'll create a new Nucleus on the chain. In this step, we register a new Nucleus instance, which is essentially a dedicated execution space on the blockchain. This gives us a unique Nucleus ID that we can reference for future interactions. Next, we'll install our application code into this Nucleus. Here, install means we'll take our Rust application, compile it into a WebAssembly WASM module, and deploy it into the Nucleus. This step effectively makes our Nucleus ready to execute the custom logic we've written. It's important to note that at this point, we can install the Nucleus either on a local node that we control for development and testing, or on the Verisense beta network, which allows us to deploy and test in a shared remote environment. Once our Nucleus is fully deployed and installed, we'll demonstrate how to interact with it. This includes sending commands to invoke the functions we've defined, for example, inserting new data or triggering custom operations, and retrieving data previously stored inside the Nucleus state. By the end of today's session, you'll have a complete picture of how to set up your environment, deploy your own Nucleus, and interact with it on the Verisense network. On this slide, we've listed the links to our official website and documentation. You can access the full developer documentation by visiting our website at Verisense Network. From the homepage, simply navigate to the developer menu at the top and select Docs to enter the documentation portal. In particular, the developer guides section covers the material we'll be working through in today's session. Everything we demonstrate today can be found there, along with additional details and references for your future development work. Next, let's start with setting up the Rust development environment. We can install Rust very easily by using the official installation command provided on the Rust website. Simply run the curl command provided in the documentation, and the installer will take care of downloading and setting up Rust along with Cargo, its package manager. The installer will also automatically configure your system environment. Once the installation is complete, Rust will be ready to use on your machine, and we can proceed to configure the necessary toolchains for building our Nucleus. After Rust and Cargo are installed, we need to configure the WebAssembly build target, since our Nucleus will eventually be compiled to a WASM module. To do this, we use Rust's built-in toolchain manager, RustUp, to install the required target for WebAssembly development. Once installed, you can verify that the target was added successfully by checking the version and using the command to list installed targets. If everything is set up correctly, you should see that the WASM 32 unknown target is now available in your environment. With that, our Rust environment is fully prepared for building the Nucleus. Next, we'll initialize our project by creating a new Rust library called HelloAVS. We use Cargo, Rust's package manager, to generate a standard library project structure for us. This gives us a basic project folder with the necessary files to get started. Here in my code editor, I have opened up our newly created HelloAVS project. On the screen, you can see two key parts of the project side by side. On the right-hand side, we have the Cargo TOML file, which defines the build configuration and dependencies for this Rust project. Let's walk through it carefully. First, we declare the project metadata, like the name and version of this crate. That's standard for any Rust project. Then we define our dependencies. The first important dependency is parity scale codec. This crate provides scale encoding and decoding. It is a highly compact binary serialization format commonly used in substrate-based chains, including Verisense. Because all the data we store into Nucleus needs to be serialized into scale format for on-chain storage, this dependency is essential. We've also included scale info. This gives our project the ability to automatically generate descriptions of the data we're using. This makes it easy for other parts of our system to understand and interact with the data structures we've defined. Next, we add VRS Core SDK. This is the Verisense Core SDK. It provides us with a set of macros and storage APIs that allow us to write Nucleus logic easily. For example, the post and get macros we will use shortly are provided by this SDK. It also gives us functions to interact with Nucleus storage, such as storage put, storage get, and storage search, which handle the lower-level storage operations for us. By declaring these dependencies here, Cargo will automatically download and compile the correct versions of these libraries for us when we build the project. Now, let's turn to the left-hand side of the screen, where we have our Rust source code. At the top, we define a simple struct named user. This struct represents the data model that we want to store inside the Nucleus. In this case, it contains two fields, an ID field of type U64 and a name field of type string. We derive two important traits for this struct, encode and decode, both provided by parity scale codec. By deriving these, Rust will automatically generate the necessary serialization and deserialization code for this data structure, allowing us to convert it into scale-encoded bytes that can be stored on-chain and later decode it back into a usable user object. We also derive type info, which is needed to include this struct's type information in the ABI export. Now, we group our API functions inside a module that's marked with Nucleus macro. This Nucleus macro is super important. It tells our system to export type information needed for the ABI. ABI files help other systems understand how to interact correctly with our module. Inside this module, there are two functions. The first function is addUser. It is decorated with the post macro, which exposes this function as a post endpoint in the Nucleus API. This function receives a user object as its input parameter. Inside the function, we calculate a new storage key for this user by determining the next available ID. We then store this user object into Nucleus storage using the storage put function. The second function is getUser, marked with the get macro. This exposes it as a get endpoint. It takes a user ID as input, loads the corresponding entry from storage, and returns the stored user object if found. Together, these two functions provide a complete minimal CRUD interface to store and retrieve users in the Nucleus. The heavy lifting, like encoding, decoding, and low-level storage management, is handled for us by the SDK and the scale codec. At this point, with just a few lines of code, we already have a fully functional custom Nucleus that can be deployed and interacted with on the Verisense network. Now that we have written our application logic, the next step is to compile our code into a WebAssembly module. We do this by building the project using Cargo, targeting the WASM 32 unknown platform. This target tells the Rust compiler to produce a WebAssembly binary instead of a native executable. It is important to highlight that we cannot use the standard default target here because our Nucleus needs to run in a WebAssembly-based execution environment, which is isolated and platform independent. Also, there is one very important limitation to keep in mind. When compiling to WebAssembly, we cannot rely on system-specific features. For example, any crates or code that depend on the system random number generator will not work because WebAssembly, by default, does not have access to the underlying operating system or hardware devices. Therefore, when writing logic for the Nucleus, we need to make sure our code is fully deterministic and does not depend on any system-specific randomness or I/O operations. This ensures that the deployed code can run safely and consistently across all Verisense nodes. Once the build completes successfully, we will obtain a WASM file, which can then be deployed to the Nucleus on the chain. Now we return to the terminal to begin the deployment process. Before we could deploy, we need to install the VRX command line tool, which is essential for interacting with the Verisense network. You can install it from its GitHub source, and it provides commands to manage accounts and Nucleus instances. Before we can deploy a Nucleus, we first need to create an account on the Verisense network. This account will own and manage the Nucleus instance and will be used to sign deployment transactions. We can generate a new account using the VRX command line tool by running the account generate command with the save option. When we run this command, it will generate a new key pair consisting of a private key and a public key along with a randomly generated mnemonic phrase for backup. The private key is stored locally in the VRX configuration directory located at home directory / VRX. By default, the file called default key contains the current private seed that is being used. The output also includes a public key and an account ID. The public key uniquely identifies the account on the network, and the account ID is used to reference this account when interacting with the Verisense chain. The VRX directory can store multiple keys, each named after their corresponding public key. The default key file points to the seed that is currently active. This allows you to easily switch between multiple accounts if necessary. By generating this account, we now have full control and signing capability to deploy and manage our Nucleus instances securely on the Verisense network. To obtain test tokens, you can interact with the Verisense Faucet bot on Telegram. The bot address is shown in the center of the screen. You can simply follow the instructions in the chat to request test tokens for your newly generated account. This will fund your account with enough test tokens to cover the deployment and transaction fees during this demonstration. The Faucet bot link is also available in our official documentation, so you can always find it there if needed. Now, let's create a Nucleus on the Verisense network. We execute the command to create a new Nucleus named Hello AVS, specifying the RPC endpoint and setting the capacity to 1. After running the command, the system returns a unique Nucleus ID, which identifies this Nucleus within the Verisense network. Here, the ID represents the Nucleus ID. The capacity parameter defines the number of validators participating in the Verisense consensus, specifically within the monitoring validator set. These validators together share a threshold private key used for secure operations. For simplicity in this tutorial, we set the capacity to 1. Next, we load the WebAssembly file we just built into the Nucleus. We run the command to deploy the WASM file, specifying the Nucleus ID, the WASM file, the ABI file which is optional, and the RPC endpoint. After submitting the deployment, you should see an output displaying the transaction hash. Seeing the transaction hash means the deployment has been submitted successfully. It's important to note that creating a Nucleus and installing its executable code are two separate operations. When a Nucleus is created, the Verisense network assigns a unique Nucleus ID, which will be used for all future deployments and upgrades of this Nucleus. While the code of the Nucleus is upgradable, the Nucleus ID itself remains fixed. Now, let's demonstrate how to interact with the Nucleus. We go back to the Verisense network website. From here, we navigate to the top right corner and enter the dashboard page. In the dashboard, we can see various information about the network, such as the status of the nodes, the current highest block height, the total issuance, and other key metrics. At the bottom right corner, we can see the Hello AVS Nucleus that we just deployed. Let's click on it to enter its details. On the Nucleus detail page, we can see all the information related to Hello AVS, including its Nucleus ID, the hash of the deployed WASM file, the creator, and other related details. At the very bottom, we can see the user struct that we just created as part of our Nucleus definition. Now, let's switch to debug mode so that we can interact with this struct. Here, we can directly perform scale codec encoding on the user structure. After filling in the necessary fields, we click the Debug button. The encoded result will be generated in both hexadecimal and JSON formats. With this encoded data, we can now directly interact with the nucleus from the command line. Another way to interact with the nucleus is directly through the dashboard. Here, we click on the Functions tab to access the available API functions exposed by the nucleus. Here, we can see the list of API functions, including the add_user and get_user functions that we implemented earlier. Now, let's first try to add a new user. For the Nucleus ID field, we can simply enter the ID of the nucleus we just created. The call has been successfully executed. Now, let's move on and try the get_user function to retrieve the data. We have successfully retrieved the information of the user we just added. Now, let's try changing the username and see how the result changes. Here we can see that the modification has been successfully applied. In addition, we can also view the generated TypeScript interface code, as well as the original ABI file that defines the structure of the nucleus. Now, let's start a local Verisense node for our development. First, we clone the Verisense node repository from GitHub. After cloning, we move into the project directory. Next, we build the node binary in release mode using Cargo. This process may take a few minutes depending on your machine. Since it can take a while, I won't demonstrate the full build process here. Once the build is complete, we can launch our local Verisense node. In this case, we're starting an Alice development node, with RPC enabled externally on port 9944. After starting the node, you should see that it has launched successfully and is now running as an Alice node. With this local node running, we're now ready to deploy and interact with our nucleus for development and testing. All RPC requests can now be tested locally against this running node. In the following tutorials, we will cover more advanced features of the Verisense SDK, including how to perform HTTP requests, use the timer scheduler, and build threshold signature scheme applications. We will also walk through how to build your own agent using the SDK. All these topics are available in our documentation. Feel free to explore and start building your own nucleus. Thank you for watching. Bye-bye.